Mohamed Bourham, thank you so much for having me here at NC State. It's a real pleasure to be in Raleigh, North Carolina.
Well, thank you so much for coming and making these interviews with all of us. I think 7 of us.
It's going to be quite a ride.
It's quite a ride. And, welcome to Raleigh, North Carolina, which is a very nicely growing city.
Yes.
And it's becoming very, very metropolitan.
When did you first arrive here?
1987.
Quite a while.
Quite a while. And this was my choice. Although I visited almost all states, but the best and all of the best moment is when I am coming back from travel to Raleigh, North Carolina.
Where did you grow up initially?
Egypt.
Egypt.
This is my origin. I was born in Egypt and I worked in Egypt. I also spent a lot of time in Europe. I spent time in France. I spent time in England. I spent a lot of time in Italy and a lot of time in Germany before coming here. And once I came here, this is it.
You loved it.
This is it.
Well, okay, let's walk through some of those places. First, you got your science education in Egypt itself?
All of my education, I got it in Egypt in the major 3 universities. So I got my BS from Alexandria University, which is a very famous university, from which all of the people in nuclear, Egyptians, are coming from there. If you actually interviewed, and I have seen that you interviewed a lot of people from other universities here in nuclear engineering. If they are Egyptians, they are coming from the same department, all of them. And, then I got my master's degree from Cairo University, which is also a very famous one. And finally, I got my PhD from Ain Shams University, which is the 3rd big university. So I moved among all 3 big universities.
Well, what's the history with Egypt's pursuing atomic technology?
Well, this actually goes back because, I graduated with my BS is in June of 1965. And I was in July, I was in the Nuclear Research Center of the Atomic Energy Authority of Egypt, which was established in almost, the 50s. And it was established for science and technology. So it is the Atomic Energy Authority of Egypt with the Nuclear Research Center. And I was officially appointed in October. So I spent the time between end of June until the beginning of October there, waiting for all of the paperwork, but officially October, I was appointed there as a research engineer in the Department of Plasma Science and Ion Sources.
And then what was the idea? Was Egypt planning on building nuclear plants?
There was actually, at that time, a reactor already in the Nuclear Research Center. It was a 2-megawatt research reactor. It is a Russian type reactor. And it was doing a lot of research. So between different departments, you can see some people working on isotope production. Some others are looking into the, basic sciences in nuclear techniques. Me, I was involved more in future fusion energy at that time. And it was quite interesting during this time that we were actually doing a lot of research. And I remember that I started publishing like 1966 or early 67. And of course, I forgot about all of these, where they are, because I don't keep copies over all of this longer time. But it was quite a surprise that I was doing some search, and that was recently, and I found that there is a paper for me that was published in 1966. Me and my advisor and the 2 Russian scientists that we were collaborating together. So I was happy and I downloaded a PDF. It looks like that they are scanning and collecting everything. And I'm pleased that we are not losing anything from our history.
It survived.
It is survived. And so it was quite a very good time that we pursued all of this research. So talking about having in nuclear, yes, a couple of years later, they started establishing what's called the Nuclear Power Plant Authority. And looking into the future of having production of electricity from the nuclear power plants.
Sounds great.
And there was a choice of the site, which is actually the site that you may hear about it right now, which will be the site for the first, group of the nuclear reactors. I think they signed a contract with Russia.
Yeah.
And so this site, which is called Ababa, it was actually established in almost, 70s. And so it's not new.
Yeah.
So the plan was there, but never been implemented. Look at the, what's happening in the area, but now it's going to be built. For the Nuclear Research Center, they updated their, nuclear facilities by having a one reactor. It's a 22 megawatt research reactor.
22 megawatts, that's pretty big for research.
Yes, it's pretty big, and they did this with the, with Argentina. So it was built under the Argentinians, and it is also used for isotope production for pharmaceuticals and the medicals. So this is what's going on there. But, my communication with there is not, on daily basis, it's from once in a while that I hear from them.
Yeah.
Yes.
And so what brought you to Europe then? You had all these countries you lived in Europe?
Actually, in Europe, we were doing plasma and diffusion research. So I was doing plasma and diffusion research with Culham Laboratory in England. And, with, also what's known as the KFR in Germany, in Jülich. So, I was doing fusion-related research.
So you continued down that fusion path, and so you've seen fusion science evolve over the last, how many decades? Where are we now versus where we were?
Right, but the thing is that, we were heavily involved when I came here in developing all of the techniques needed to support the future of the fusion energy. And of course, it was the time that the international, system started to show up under the name ITER, I-T-E-R.
Yes, ITER.
And so we became involved with the Department of Energy. Me and my colleague, Professor John Gilligan, who is currently our, executive vice dean for research and graduate studies for the College of Engineering. So we were partners in this. And we graduated so many students, working on specific problems related to the problems expected in this ITER, like, for example, the effect of very high heat flux on the components and the materials, how, if an abnormal event would happen, what's going to happen when we have an aerosol, for example, spreading in the entire vacuum chamber? So we did a lot of work, even at some time, because, of course, the level of funding was not that great. So that's why we started to diversify in something different, and we were heavily involved in electrothermal plasma sources. Electrothermal plasma sources is something that we started with Department of Defense. And it was a concept that allows for, propulsion systems. And it was also considered as a pre-injector for what's famously known as railguns.
Railguns, yes.
And so we get very highly involved in doing research for the concept and the materials needed to survive this environment. This was work that we have done with the Ballistic Missile Defense Organization. We did the work with the Strategic Defense Command, the Army Research Office, Army Research Laboratory, Office of Naval Research Laboratory. It was really a good period of time through which we produced a lot of research for electrothermal plasmas and its propulsion.
And what is the research exactly? Is it you're trying to understand how materials behave? Are you trying to understand what the behavior of the plasma itself is?
Both, because we understand the impact of these sources and its performance on the integrity of the materials from which we are building the sources. And, because it's subject to very high heat, very high pressure, very high, exit velocity. So we are talking about velocities in terms of several kilometers per second. And actually, many of the Department of Defense vendors were doing also research, like United Defense, for example. They were doing research and producing a lot of systems in which we were involved in many research related to them. But also, we took this research into the fusion arena. Why? Because if we can get very high propulsion, then we can use it as a fueling mechanism for fusion reactors by accelerating frozen deuterium to speeds like 2-3 kilometers per second, so we can get the fuel to the core of the fusion reactor before it evaporates.
And this is like an impact fusion of some sort? Is that how the fusion energy happens?
In the fusion reactor, of course, the fueling needs deuterium and deuterium tritium, but how to get it to the core? The core is very hot. And so we have to get it into the frozen form, and then we can accelerate using an electrothermal plasma injector so we can get it to the core.
It's like a pellet gun for the fuel.
It's a pellet fueling. And this is for the deep fueling of the system. In fact, we have done a lot of computational techniques also, and we developed, codes for this. And so we were doing, all sorts of experimentation and computational as well. Recently, and as we speak last year, so I graduated one of my PhD students who was actually shuttling between North Carolina State University, Oak Ridge National Laboratory, where there is an electrothermal gun there.
Yes, I've seen them.
Operated by a former student from University of Florida. But, he was in communication with me for each single step in building the electrothermal source. And my student was also shuttling to San Diego, California, to go to General Atomics to run experiments on their tokamak reactor. He finished all of this. He did very good, beautiful amount of work. There was a choice of postdoctors for the ITER.
Yeah.
They choose, and they announced that they will need to hire 5 postdocs. One of them will be from United States. He was the chosen one. He is now in Cadarache, France, doing all of the research and experiments in ITER. So we were doing this all the time, and we still do a lot of research in electrothermals. But additional to this, I also took another branch, and this other branch goes to radiation and goes into waste. Because waste is a serious problem, and we want always to look into waste, especially what's known as dry casks, where you can get the spent fuel to be inside of the dry casks. So we get into this research by providing techniques like, various coatings that provide various barriers, different forms of the concrete, not the standardized form of concrete. And we got into this, and we are doing, extensive research in concrete forms. Even we have a company that's making specialized forms of concrete, working with us. And we are doing a lot of the radiation shielding studies specifically for the dry cask. So we got ourselves into another domain. So here, me and my students, we are not just focused on the plasma. Now we have plasma as one of our activities. We have shielding as another activity, and we have coating as another activity, and all of these are really very strong and good. And recently, we got a new contract with Department of Energy in which we are looking into non-intrusive sensors that can be used in any nuclear environment, including reactors, where the sensors will not be inside of the reactor vessel. No, it's from outside.
And what are they detecting? How do they?
They detect based on having the piezocrystals. This is the form of the sensor. The piezocrystal is activated from outside. And with a technique, it launches a surface wave, and the surface wave will propagate. And then we have a detector also outside. Through this path of the surface wave, we get measurements of phase change and signatures. That's really a function of the interior temperature.
Yes.
And the pressure.
So you're correlating the effects on the outside to what's going on
to
the inside.
what's going inside.
And since we have sensors on the inside right now, we've got a data source
there.
You
can correlate.
And we just match them.
Yeah, you can match them.
Some sort of function, and then we don't need the stuff on the inside anymore.
Yeah, and we do this. It's a contract with Department of Energy that we were awarded almost a year and a half ago. So currently we are working on it. And it does include, one of my colleagues from mechanical engineering. He is the lead PI. And one of my colleagues from electrical engineering, you see the link, and myself, and one of our colleagues from Penn State University. So we put all of these pieces together.
And what characteristic of the internal conditions are you measuring? Is it neutronic flux? Is it heat? What are you?
We are specified into measuring the temperature, the flow
of the water,
of the coolant.
And are you actually mapping how the flow moves, or just doing a rate?
The rate.
Okay.
And the level.
Okay.
So the flow rate, the level,
so this would be for like a boiling water reactor or something, where you want to know where the phase change, what height the phase change exists.
And the pressure. So these four parameters are the...
So the pressure makes the most sense to me because it's a piezo crystal that measures pressure, outputs current.
So this is really very focused on this kind of research. And we are doing this with the Department of Energy. It's under a program known as NAUP, which is Nuclear Engineering University Programs.
Yes.
And it's a program that's
it's a grant mechanism.
Yeah, it's going every year. And, it is the major support to all nuclear engineering programs in the United States, and as well as to some other departments like maybe mechanical engineering, electrical engineering. If they have something related, they apply.
Listen, the whole thing with nuclear is it's so cross-disciplinary. There's chemistry involved too.
Yes, there is chemistry involved. So this NAUP is very good. And we are, pleased that we are partners in many of these activities with them. There is also infrastructure that we can get. Like, for example, we can submit for equipment, that we need to buy this piece of equipment. And if they, see that it sounds, they award us. Yeah. So we got, for example, several before. The first one, it was like maybe 8 years ago, we got a dual, ion beam irradiation system. And then we got last year, we got, an autoclave stress corrosion with me and 3 of my colleagues. It was led by Dr. Kawomi.
You said autoclave stress corrosion?
Yes.
So this is like a giant oven of some sort?
It's a giant, it's a very good piece of equipment. And recently this year, we got another one, Dr. Yang and myself, also on, equipment for making a specialized form of radiation detectors. And it needs, glove compartment and things like that. So through all of this, the research is going into the right direction. And as you can see that we are diversifying our, our effects. Of course, as you can see that we are doing a lot of materials studies here.
Materials is everything.
It's everything. So when I talk about electrothermal plasma sources, there is a lot of materials into it. Yes. When I talk about radiation and canisters, for example, and the dry cask, there is a lot indeed of materials, including concretes. The people, needs to understand that the concrete is one of the most beautiful materials.
And tell me more. How do we think about concrete?
For example, we sensitize and look to sensitizing concretes with different aggregate. So standardized form of concrete is coming from Portland cement.
Yes.
And the mortars.
Yes.
And of course, you blend with gravel or
aggregates,
whatever, sand. And it has a different, standardized formula to make the concrete. But we add some other materials here. Maybe we wanted to add some bismuth. Maybe we wanted to add some lead. Yes. Maybe we wanted to add any form of glasses.
And what does it do? How does it change the properties if you add these things?
Now, if I use the standard form of concrete, I may need, let us say, I may need for a certain case that I have, some kind of radiation, so I need to shield this, and I may need like 2 foot. Mm-hmm. All right? But if I sensitize different materials, I may actually get, the same attenuation for less thickness, which means a reduction in the mass and a reduction in the cost.
Can I ask you a question?
Yeah.
Yes. When it comes to radiation protection and structural materials and concrete barriers and such, since let's say that your barrier to the outside world doesn't need to have excessive strength, you just need the radiation protection, how come you don't just have like concrete wall, a few feet of sand, just normal sand, and another concrete wall, both 6 inches or something, and then you can vary as much distance as you want for radiation protection without having the additional cost of producing that concrete structure? Why not just fill things with sand? Is sand not good for radiation protection?
It's not going to do what we need because it is a matter of the specific density of the material, because there is something known as linear attenuation coefficient, and it is a material related characteristic.
Yes.
So it is highly dependent on the material. And then you can transfer this into what's known as the mass attenuation coefficient. Once we say the mass, it means that the specific density of the material is now included. And so we need something that can give us really a high mass coefficient that can stop and or reduce or attenuate
so you make your concrete a mixture of different elements, and some of those elements have a higher linear diffusion coefficient, and so by making that mixture you can kind of average it in there somehow.
And you wanted to get, if you can synthesize and they get, for example, better attenuation for the same thickness, good. Or if you can get the same attenuation for less thickness, it's also good.
Yes.
If you can get better attenuation and the less thickness, it's even better.
Yes.
And so this is all what's going on. And actually, I have seen recently a lot of research ongoing into concretes and the sensitized concretes, and even adding some glass components into it because of the elemental composition. And it's going really very well.
Let me ask, how do we think about this attenuation coefficient? Is it just a function of the density of the element, how much the element weighs? Is it the higher you go up, the better coefficient you have?
It is highly dependent on the material itself. There is a famous law, which is an exponential law, telling you that it is going exponentially with the negative of mu xx is the thickness. And the mu is the linear attenuation coefficient, which is material dependent.
And how do we, is it each, how do we know what element has what?
We measure.
We measure. But is there a way, is it predictable? Is it a function
and it is predictable too.
Is it a function of atomic mass and, or are there other components as well? Is the lattice structure of a function as well?
It is a function of, what we call it, how interactions, take place. There is a photoelectric, effect. There is a Compton effect. There is, there is also the, some other means, Compton effect is one, and the photoelectric is one, and the pair production is one. And so the linear attenuation coefficient is the sum of all three.
And are we talking about for neutron radiation or gamma radiation, or both?
For gamma, actually, gamma radiation and the neutron radiation both are obeying this similar law. But when we talk about,
But the neutron radiation is also a function of the cross-section.
It is.
Yes.
It is. That's why it is material dependent.
Yes, yes.
It is. And here you can see that most of the focus for the waste storage is more focusing on the gamma more than neutrons.
Right, because waste doesn't produce neutrons.
Yeah, we have the neutrons, for a spent fuel, and it has, an average between 1 to 10 mega electron volt neutrons inside in the canister. And that's why we say that the average is about 2 MeV for all. But this is inside of the canister, which is stainless steel.
Yes.
Now let us come to the gamma. The gamma, this is just in the waveform, and this photon transport. And so gamma is the main thing that we look at, because also gamma produces heat. So here in a dry cask, we have the spent fuel, we have inside of the stainless steel canister, there is an air gap, and then there is the concrete.
Yes.
So all of this pathway is really looking into the gamma all the way until we get outside, and we can calculate the dose rate outside and get sure that the dose rate outside is within accessible limits.
And how come we don't just, instead of putting it in a cask and everything, how come we don't just drop it to the bottom of a lake somewhere? We have plenty of lakes that are already chemically toxic or too salty. No one would ever go inside. Why not just drop it all to the bottom of the lake?
Well, the point here also can go very well political.
It's just political, not technical.
It can go political. For example, the Yucca Mountain site is a beautiful site as a repository. And it is, under the Yucca Mountain, where you have, the entry, and then you go all the way down.
Yeah.
So it's almost like 3,000 feet.
Yeah.
And then you have tunnels.
Yes.
And you have vaults.
Yes.
And so it is a beautiful site, and it took a lot of work in the building, but of course the state of Nevada, or the people of Nevada, got to, actually
block it. Why do we even need that level of depth and tunnels and protection?
It's better.
But doesn't your average coal pit, just a pit that you would dig coal from, isn't that already pretty good from a water intrusion perspective?
If you wanted to put it anywhere in the bare area, you will get the strong opposition, because you don't want the people to
say... But political, not technical.
Well, technically, of course.
Like any coal pit, why is it a coal pit?
For example, most of the spent fuel remains in a large pool in the site where you have the nuclear power plant for as long as it takes to cool down before transporting into the casks.
Yeah.
And the casks maybe just, can be in a cask site that's even within the premises of the nuclear power plant.
Yeah.
But the repository is giving you more safety.
And why do we need more safety? Is it not the dry cask on site? Is that not safe enough?
It is safe, and we have done a lot of studies that showed that most of the dry casks are performing very well. Of course, you want some of the dry casks, depending on the fuel, inside, that it will be, good for 300, 400, 500 years.
But to me, it seems that if it's good for 300, 400, 500 years, that's the solution.
Yeah.
Because humanity, 300, 400, 500 years from now, will have much better materials, much better this, much better that. And on top of that, the money that you would spend up front, if all you were to do was put it in a bank account and let the interest accumulate for the 100, even 100 years, it would be a mind-boggling amount of money. So it never makes sense to spend the money up front if you have a 400-year solution ready to go. Just put it in the dry casks.
Well, I like dry casks, and I think dry casks are really very, very good, technique. And, I have seen a lot of them, and I do work and the modeling on many of them, and I think this is very good. In collaboration with some of my colleagues from Idaho National Lab, because they have dry casks on their sites, and one of the dry casks was opened after, I think, so many years, like maybe 20 years or so, to check and to see if there is corrosion, if there is, just for inspection, because usually the top hatch never been opened for dry casks. Once it is sealed, it is sealed. But there was one inspection that was done, and they wrote a report about it, and everything looks good.
Yeah, so what's the problem?
It's everything looks good, and the dry casks actually performed very, very well. So this was very pleasant. All what we needed to look at is, for example, can we make, less concrete instead of thick concrete?
Yeah.
Do we need, any kind of liner inside that can be, a heat absorber? So all of these are techniques that we are looking at.
Yes.
But I think, in my opinion, that dry casks are beautiful.
Yeah, beautiful. Perfect. They're perfect. Anything that buys you 400 years is perfect. To me, it almost seems irresponsible to spend the billions of dollars even investigating Yucca Mountain now, instead of putting that money into children's health care, instead of putting that money into a bank account just to accumulate more interest. It seems crazy to spend that money on a 1,000,000-year solution when we have a 400-year solution that's already taken care of.
Well, you can see the mix between science, technology, and the politics, and how things can get into, fractions. All right, here is the science in this pan, and it's technology, and here is the politics and the money, and then look to the balance and see what you can do. So it's like this, and of course the debates will be continuous always. But for us as researchers, as long as we are satisfied with dry cask solutions, it's good. And even transportable casks, it's good. And we provide additional, features, as I say, that we look into best thermal barriers inside.
Yes.
We look into maybe best materials instead of just stainless steel, maybe, some special alloying. We look also to best formalism of concrete and the concrete, compositions.
Yes.
And, all of this will be endless form of research that we are doing. And it actually gets, a lot of good activity for us as researchers, for our students, for their research, whether they are doing a master or PhD, and in relation to industry that can benefit from what we are doing. Like, for example, we have strong talks with Savannah River, for example. All right, and we have also some talks with people in Los Alamos and some others because of the site in Hanford, So we look into all of this to provide solutions. And I think that it is time now that was given with very good focus on nuclear waste, because it was not really given this kind of interest for some time now. There is good interest into nuclear waste and waste forms, and how can we handle all of this.
And so is that your primary focus right now, nuclear waste, or you still do stuff with plasmas and fusion? And
I have currently, because over the past 3 years, so I graduated 5 PhDs, and they are gone. And so 2 of them were working heavily on the plasma from the form of electrothermal plasmas. And one was heavily involved in corrosion studies. And so, like stainless steel coated with different materials, also for canisters. So we were exploring the technique of the corrosion and the technique of which we are doing the coating. And one was involved in modeling, all right? And the last one, the one I just mentioned to you, he was heavily involved in fusion, but using also some form of ceramic materials specifically. Now I have 4 students with me. One is heavily focused on concrete and, concrete forms. One focusing on also another formalism for concrete and the coated materials, and one in electrothermal plasmas, and one is looking into the sensors and non-intrusive, embedded sensors. So, we are still having all the 4 right, directions, and all of these directions provide this very nice formalism of, multidisciplinary, interdisciplinary, and in the meantime, the diversity in research. So they are moving all in these directions.
Can we talk about materials and fusion for a second?
Yes.
So when I think about the sun, right?
Yeah.
The sun is like your perfect fusion device because you don't need materials, you have gravity to hold it all together, essentially, right?
Exactly.
And it's almost, it's like, is it a perfect sphere, the sun, or how is it in terms of shape?
The sun in its shape, it's almost very close to a perfect sphere. And the reason for this is because it is a gaseous formula of hydrogen, and because of its a huge mass, so the gravitational force is huge. And so it gets all of this very nicely distributed and homogeneous. So yes, it's close to a sphere.
But that's what I wanted to talk about.
Yeah.
Because it's not always homogeneous. You've got solar flares.
Oh, yes, of course, from the sides, and yes.
So if we have this like perfect, gravity structure holding it together as close to a sphere as possible, and it still does flares, how are we going to deal with fusion inside a reactor and controlling its flares?
Oh, no, we don't do it with gravity because we don't have the luxury of having the gravitational force.
So how do you control it?
We control using magnetic field.
Yeah.
So the magnetic field provides 2 things. The magnetic field provides a form of a pressure. So it actually pressurizes and squeezes the plasma, all right? And the magnetic field also provides the form of and that's what we call confinement. It confines the plasma. And it exerts the pressure because it is forcing all of these ionized species to rotate around the field line, so they cannot escape. And as you intensify the magnetic field, you get the radius to be smaller and smaller, and you can control the particles. Part of the study that we do is that what if at some given point that there was a sudden failure in the magnetic field?
Yes.
So this means we call it disruption.
Yes.
So if this disruption happens, then all of these particles will find their way inside and to the walls. So here we get the impact with materials Here we wanted to study the response of materials to the high heat flux coming from these species if a disruption event would take place. And this is a very good part of the study that we are doing.
And then what is the scenario in that case? If you've got this disruption and you've got a heat flux that shoots out, do you just shut down the fusion reaction?
Well, temporarily.
Yes.
Temporarily. But it is expected that, the frequency of disruption, there are some controls that you can, because it is not one magnetic field. You have actually 3 magnetic fields for this kind of reactors, famously known as tokamak reactors.
Tokamak, yes.
And, so there is some features with which you can do, suppression of the disruption, so it is not at a high frequency to happen. This is a part of challenges in fusion reactors.
What are some of tell us about some of the challenges so we can identify where do we put PhD students, where do we put labs efforts, what are the different challenges that you see?
Of course, some may be, very highly involved in the magnetics because these magnets are huge. And actually it is an amazing engineering achievement. Let us put it this way.
Yes.
It is an amazing engineering achievement to make this kind of magnets. And of course, the entire reactor has a donut shape.
Yes.
Right? With these magnets surrounding.
The tokamak has the donut.
It's a tokamak. The materials is an important part from the first wall inside to the bottom where it is the diverter from which you extract the energy and you get the ash. So here, this diverter attracted the attention for a lot of studies on the material, whether, it has to be with graphite, for example, what kind of coolant channels you have, even looking into the entire inner of the device itself. The unit that's built in England under the name JET, G-E-T, Joint European Torus, it is beryllium. So it's all beryllium inside.
Beryllium?
Beryllium. Because it is a very low Z material in the beginning of the table, all right? So it's light. But given the fact that also beryllium is toxic, because it's vapor is very toxic. And, some others, the one that was built as a test also facility in MIT, it was, a tungsten. It's all tungsten.
Highest melting point of any material.
And the one that's operational by General Atomics in La Jolla, all right, which is, usually we say San Diego, but actually it is La Jolla. It's actually graphite.
Yes.
It's graphite. So you see that, study of the materials for fusion reactors extended over large amount of time, 2-3 decades, just looking to materials between what should be on the diverter, what should be in the first wall, whether graphite is a good material, beryllium, or whether we go with heavy metals. So all of these are part of the material study for fusion reactors, including, of course, the interaction, not only from the heat flux point of view, but the impact of the charged particles as they are impacting on the materials.
What is the impact of the charged particles?
Well, there will be, if the reactor is operating using deuterium-tritium mixture, then there will be a production of alpha particles, heavy, which is the nucleus of helium, and there will be neutrons also produced.
Yes.
And the neutrons at 14 MeV. So all of this, can do a neutron impact. So there is, part of what traditionally we know in fission reactors about, neutrons impacting on materials.
And then are we worried, if the neutrons impact at 14 MeV, are we worried about it like breaking off the outer layer of your material and that entering into your...
It causes what's called, irradiation. It's a neutron irradiation of materials. And there is a lot of studies for neutron irradiation of materials for so many other, things, for all of the entire arena of fission reactors, for so many other applications. It is really, the irradiation that causes, materials hardening, for example, cracking, for example, swelling, for example. So there is a lot of effects. And, this also, expected to happen in future fusion reactors because you have neutrons.
And has the industry coalesced on a material solution for the inside of a tokamak reactor?
It's mostly coming from the research that was conducted under the auspices primarily of the Department of Energy, and General Atomic is one of the companies. It's a big company, and they are doing a lot of research related to fusion materials, and they are operating their own tokamak, and they call it the National Fusion Facility. Because it is really under operation daily.
Yes.
Daily.
As we wrap up here, maybe you could project, based on your wealth of experience, having seen this industry grow up over all these decades, could you put your magic hat on and tell us, what does the world look like 10 years from today?
I think in 10 years from now, the world will start seeing the first test reactor. It will not the one that will be producing energy to the grid, but it will be the test reactor that proves that the feasibility is there. And yes, you can run it, you can control it, and then you can move into the commercialization. So within 10 years, I would expect that this will happen. 10 years, maybe 15, but in the history of the human race, give it the time. Nothing happens overnight.
Mohamed Bourham, thank you so much for your time. This has been a
thank
pleasure
you
of a
so much.
conversation.
My pleasure as well. Thank you so much.